discussing how these coherent states are the best quantum description of classical oscillators. We know that the coherent states, they have been defined as superpositions of number states along with a certain complex amplitude alpha h power n factorial under root, where n goes from 0 to infinity. So the coherent state really is a superposition of the number states. And we also noticed that this state is not an ideal state of the Hamiltonian, so it evolves with time. So with time, the state is given by alpha e minus I omega. So it's still a coherent state, although with a different complex number association with it. And there is an e raised to minus I omega t over 2 factor here, right? यहाँ 2 है. So this is our coherent state and how it evolves with time. Now what we would like to see, what does the state look like? And how are we claiming that the coherent state, which is no longer an ideal state of the Hamiltonian, how does it qualify as an excellent approximation to a perfectly classical oscillator? We also know that the Hamiltonian for the harmonic oscillator is h bar omega a bracket a plus half, or h bar omega, the number of a plus half. This is something we already know. So let's first of all try to find out the expectation value of the coherent state, of the time dependent coherent state. Remember that for number states, for get n, the expectation value of x is going to be the same as the expectation value for the momentum operator, and this is 0. So for all number states which are ideal states of the harmonic oscillator, the expectation value of the position is 0, and this is something really obvious. The first Hermite polynomial is just a logic. This is the ground state. This is the second Hermite polynomial. This is the get one state. So this is the n equals the second number state. This is get 1. This is get 0, and so on. So all of these number states have an expectation value for the position operator, which is 0. The expectation value for the momentum operator is always 0, and you can explicitly work these out, but they are quite obvious. For this Gaussian state, the expectation value of the position is 0, and so is the expectation value of the momentum. You find the Fourier transform of this wave function, you get a wave function in the momentum space with an expectation value of 0. So the expectation value of the number states is 0. And that is as it should be, because if these states are ideal states of the Hamiltonian, they don't change with time. So whatever the expectation value is at time 0 remains constant. It's a constant of motion. It remains constant with time. But this is not the case for the coherent states. The coherent states are evolving with time. So what we are interested in is finding the expectation value of the position operator. Now this is given by bra alpha x get alpha, right? And we know that this x is really h bar over 2m omega bra alpha a plus a alpha get alpha, where these alphas are now time-dependent complex numbers. Later we'll see what is the physical significance of this alpha. So I've written the position operator in this dimensionless basis, which is spanned by the operators E and K dagger. And now I can simply find out this inner product. Now what I could do is, I know that alpha is given by ket n, alpha is for n factorial, n goes from 0 to infinity. Now if I apply the raising operator on alpha, n 0 to infinity, alpha raised to power n factorial, alpha raising operator acting on n. Now what is the result of this raising operation? This creates n ket n plus 1 under root n plus 1. Correct? Likewise, lowering operator acting on alpha. What is the result of the lowering operator acting on alpha? Asad? It's just alpha. Get alpha. Because the coherent state is an eigenstate of the lowering operator. Okay. So I can just plug in these values. Expectation value of x turns out to be h bar 2m omega alpha is alpha get alpha plus n goes to 0 to infinity alpha raised to power n factorial under 2 with n plus 1 n plus 1. So this turns out to be h bar 2m omega. This is a big bracket here. Now of course this inner product is simply alpha plus I would like to write the dual of the coherent state. So I write n goes from 0 to infinity. This alpha is replaced by alpha complex 1 raised to power n factorial square root raw n, and I would like to find its inner product. Therefore, I would write this factor here. N goes from 0 alpha is for n factorial n plus 1 Up. What do I do about this product, inner product? only exist when n equals n plus 1. Right? So you can work this out. Expectation value of x is h bar 2m omega under root. Alright. Now this is the creation operator acting on alpha. This is the lowering operator acting on alpha. Right? So this turns out to be, that's why this is alpha here. ठीक किया था मैंने alpha plus. Now this only exists. So this is a series. This is a series. You only have to add up the terms in which n equals n plus 1, because otherwise this inner product will vanish. There's a Kronecker delta between m and n plus 1. So what I would like to do, I would like to write alpha star m must equal n plus 1. So alpha star n plus 1 here. I will sum over all values of n. N goes from 0 to infinity. Right? For example, when n equals 0, I will get 1 here. So I will take the inner product of the same 1 with 1. So I will have alpha star m equals n plus 1. I will have an alpha is for n here. Right? M plus 1 factorial, m becomes n plus 1 factorial. This is n factorial here under root, and inner product of, so it only exists when m equals n plus 1, and when m equals n plus 1, this inner product is just unity. And then there is the under root n plus 1. Okay? So this becomes h bar 2m omega alpha plus infinity alpha modulus is for 2m alpha now. This is, now what's the result of this? This is n plus 1, this is n plus 1 factorial. So this is n factorial, right? N factorial squared under root n factorial without this square. Alpha star is for n in alpha n. This is alpha mod square is for n. What is n plus 1 with n plus 1 and alpha star, right? Okay? Now what does this become? This becomes h bar 2m omega alpha plus alpha star n goes from 0 to infinity alpha mod square raised to power n divided by n factorial. Okay. Now what does this term equal to? So I have h bar 2m omega square root alpha plus alpha star e raised to power Correct? So I can write this in the following form. Expectation value of the position operator is h bar 2m omega. I will take alpha e raised to minus alpha mod square over 2. Let's take this as common. This becomes e raised to minus alpha mod square over 2 into alpha plus e raised to alpha mod square over 2 alpha square. Correct? Now this is a complex number and this is a complex conjugate. This number is just real. So a real number is being multiplied by a complex number. I have a complex number here and I have its conjugate here. Right. Oh, this is a time dependent factor, right? This is a time dependent factor, which means that this is alpha t. This is alpha t. This is alpha t. Okay. So I also have to take into account the time dependence, which I am not doing for the time being. So what I've written here assumes that this alpha t is going to, this is constant with time, isn't it? But I have some time dependent factor here, right? And I have a time dependent factor here. And what is that time dependent factor? That time dependent factor is alpha e raised to minus I omega, isn't it? So I need to put in an e raised to minus omega t's in here as well. It's complicated. So let me try to do this with another approach. This, I have to put in time dependent factors here. So this approach is going to get complicated. Let me try another approach. Let's look at this. If I have the lowering operator acting on alpha, I get alpha, right? This is time dependent and so is this. Okay, if I take the dual of this, I have alpha A dagger. This is a complex conjugate T alpha T. Okay, so if I want to find the expectation value of x, I can write h bar 2m omega alpha A plus A dagger get alpha. So this first term, I operate from the left on get alpha. H bar 2m omega. Now when I operate this lowering operator, lowering operator on alpha, I get alpha, which is now time dependent, alpha d, alpha alpha. Now this is time dependent, this is time dependent. But the state is always normalized during the time evolution. So I have, this becomes equal to 1. For the second term, I operate from the right. I use this expression. So I have alpha star E alpha m. Right? So this is a much easier approach. So this is one, this is one. Now this is time dependent and so is this. So I have h bar over 2m omega alpha plus alpha star. And both of these are time dependent terms. So I go here, the expectation value of x is h bar 2m omega. Now let's suppose that our alpha, which is time dependent, has some magnitude alpha and it has some phase. Okay? And this phase in general can be time dependent and its magnitude can be time dependent. So all this time dependence in this. So I can write this expression as alpha. I can take this as common. I have E, right. And we also know that this, if you would like to explicitly put in the time dependence, let's explicitly put in the time dependence. It's a minus I omega theta. Okay, so now this alpha becomes time independent and this delta becomes time independent. So I would like to make the phase time independent and I would like to make the amplitude and the phase time independent. So I explicitly put in whatever time dependence I have. This time dependence we derived in the previous lecture and it comes from here. This is my alpha as a function of time. So if my harmonic oscillator exists under this Hamiltonian and I prepare a coherent state starting off with a value of alpha given by alpha 0 or with alpha naught. So this is how the alpha changes with time. This is how the complex number changes with time. G factor. So let's explicitly put in the time dependence separately, and this becomes the time independent amplitude, this becomes the time independent phase. So under this prescription I have alpha is equal to Ei delta E minus I omega t with a time independent magnitude, and this alpha star becomes E minus I delta E plus I omega t. So this expression can then be written as h bar 2m omega magnitude of alpha 2 times cosine of delta minus omega t. Alright? Or h bar 2m omega 2 times magnitude of alpha cosine of omega t minus delta. Because the cosine is an even function. So this is how the expectation value of a coherent state changes to time for the momentum. If I plot this expectation value versus time, so here I have time, here I have the expectation value of the position operator, right? I'm trying to measure the position. Each time I get a wave function, this is the expectation value. This plot look like this. It's a cosine function. So this is our first idea that this coherent state is actually oscillating in time. But what we know from this result is we only know this far, that the expectation value of the position is oscillating in time. We don't know what the wave function is. So the wave function can be changing. All of these wave functions are different wave functions, but they have the same expectation value for the position. Alright? So we don't know what the wave function is. What we know is that its average value for the position is oscillating with time. So this is our first approach towards saying that the coherent state is an oscillator. But really we don't know how is it oscillating. We just know that its expectation value is changing with time. Likewise, we can determine the expectation value of the momentum. To perform a similar calculation, expectation value of the momentum operator minus iota h bar with a factor of 2m omega, right? This is the momentum operator. Is it so? You tell A minus A dagger minus 2m omega h bar minus iota e, right? This is momentum operator. We have alpha here, which is time dependent, A minus A dagger alpha. Now exactly the same calculations will be repeated. The only difference here is that here we will have a negative sign. So I will get minus iota 2m omega over h bar with alpha minus alpha star. This is the expectation value of the momentum minus iota 2m omega over h bar, amplitude of alpha 2 iota sine of delta minus omega t, expectation value of the momentum. This minus iota multiplies off with iota to give me plus iota square minus. I can take this minus inside. When I take this minus inside, I get a sine omega t minus delta. So I have 2m omega h bar sine of omega t minus alpha, of course with a 2 here and an alpha magnitude. Where minus I and then you are multiplying it by I. So I get minus I multiplied by minus iota square. Minus iota square is plus. Okay, so I can put a minus here. Alright. So if I plot the expectation value of the momentum operator, it's 90 degrees out of phase with the expectation value of this operator, of the position operator. So this is the expectation value of the momentum. So in summary, I have the expectation value of the position operator, which is given by, let me write this down again. I have 2 modulus alpha h bar 2m omega. Now remember, what is this alpha? Is this time dependent? This alpha that I am written here is time independent. Alright. Or in other words, this alpha is time independent because whatever alpha you started off with, if you take the magnitude of the alpha, it remains constant. It only acquires a phase. So this is, you can take this to be time independent or dependent. It's independent of time. You can put in a time factor if you like. So this is just the amplitude, and the amplitude for alpha remains constant even when the coherent state is evolving in time. The coherent state is evolving in time, we know that. The magnitude of alpha remains constant, it only picks up a phase factor, right? This is just a phase factor here. This alpha is just picking up a phase. It's just a phase. Okay. The original alpha can indeed be a complex number. That is why we have a delta as well. So the expectation value of the position is 2 times the magnitude of alpha, this factor, into cosine of omega t minus delta. Now what is this omega? If you look at the harmonic oscillator and look at its quantized levels, you created a superposition of all the number states. This is what the coherent state is. with each coefficient finely tuned, and omega is the separation between any two adjacent levels. So now this object has an expectation value for the position that is oscillating with time with the frequency omega. This omega is the difference in frequency between any two adjacent levels of the harmonic oscillator. Right? So we are getting the semblance of a classical oscillator. Likewise, the momentum operator is minus 2 alpha 2m omega over h bar sine omega t minus delta. Now these two operators, x hat and phi hat, we know that they are conjugate variables. They are conjugate observables, incompatible observables, and they satisfy the uncertainty relationship. Right. And they are 90 degrees out of phase. So they are also called quadrature observables, especially when we talk about them in quantum optics. They are called quadrature observables. So for a coherent state, these expectation values are oscillating in time. What we are now interested in finding out is what is the wave function looking like with time. Of course, the wave function is not constant. It's not a constant with time because the coherent state is not an eigenstate of the Hamiltonian. So it's of course it's changing with time. Okay. So instead of finding the wave function of the position space, I would like to know instead what is the expectation value of, what is the uncertainty in the observable x. And I assume it's a function of time. I would like to also find out what's the uncertainty in t. I assume it's a function of time. And from this I will obtain a very useful result. So let's find out the uncertainty in the position. We know that this delta x squared is given by the expectation value of x hat squared minus the square of expectation value of x. Right. So let's try to find out the expectation value of x hat squared. Now my x is given by h over 2m omega. The coefficient is h bar over 2m omega. So just square this, I get h bar over 2m omega. I have alpha, which is of course a function of time, right? I have a plus a dagger twice a plus a dagger alpha. Correct? So I just expand this out. So let me just focus on this one. So alpha a square plus a dagger square plus a dagger plus a dagger a. Alright. Now let's look at the first term. When the operator A acts on alpha, this alpha is an eigenstate of the operator A, the lower operator. I get alpha. So acting once I get alpha, acting twice I get alpha squared. Okay. Now when A dagger acts on this bra alpha, I get alpha conjugate. So we get an alpha conjugate square term. Now when this if I look at this term, what I would like to do. So let's look at this term. A acting on alpha gives me alpha. A dagger acting on alpha gives me alpha complex conjugate. So I get an alpha modulus squared here. So let's look at this term. Alpha, A dagger, alpha. Now we know there is a combination relationship between A and A dagger. This combination relationship says this is equal to 1. This is A dagger minus A dagger A. So I can write this A dagger. This A dagger as 1 plus A dagger A. So I get a 1 here because of this one. And then A dagger A. A dagger A is simply another instance of this. This A dagger A gives me alpha mod square, so I put it in 2. So what is this really equal to? This equals h bar over 2m omega, and this term that I've written here, this thing, is simply alpha plus alpha star squared plus 1. Okay? Similarly, let's find the expectation value of the momentum squared. Now the momentum operator is minus iota 2m omega over. So I have to square this now. I get plus iota squared, which is minus 1. So I get minus 2m omega over h bar here, right, without the square root. Alpha A minus A dagger squared. A minus A dagger. So I can't just take the square because these operators don't commute. I have alpha here. So I would like to find out this thing. This thing once again is A dagger minus, it's A squared plus A dagger squared minus A dagger minus A dagger A. So the only difference is that I have a minus here and I have a minus here. Okay. So I will get a minus here and I will get a minus here. So the result of this computation is minus 2m omega over h bar alpha minus alpha star squared minus 1. ये कैलकुलेशन करके देख लीजिए. Now what is this alpha plus alpha star equal to? Alpha plus alpha star is simply 2 times alpha work this out. This is alpha modulus E I delta E minus I omega t plus E minus I delta E plus I omega t. This is 2 times alpha cosine of omega t minus delta. Just the 2 times the real part of alpha. Likewise, alpha minus alpha star is simply 2 iota times alpha sine of omega t minus delta with a positive sign or with a negative sign? With a negative sign. Because I defined my alpha to be I plus delta. Alright. So instead of alpha plus alpha star, I can write this thing here. So my expectation value for x square or my uncertainty for x squared is simply this term h bar 2m omega, the square of this, which is 4 alpha mod square cosine square omega t minus delta plus 1. And from this I subtract the square of the expectation value of x, which is given here. So h over 2m omega 4 alpha square, they come out from here. This comes out from here. Minus cosine square omega t minus delta. This goes away. I'm left with 4 alpha modulus squared h bar over 2m omega. So this is the square of the uncertainty in the position variable. Let's find out the square of the uncertainty in the momentum variable, delta p squared. Delta p squared is just this term minus 2m omega over h bar. Instead of alpha minus alpha star, I put this. The square of this is 4 iota square, which is minus 4 alpha mod square sine square omega t minus delta. And from this, I have to subtract this object, the square of this. The square of this is plus 4. Right? This minus comes from here, from the similar minus to this one. I have minus 4 alpha mod square sine square omega t minus delta. So this minus goes away with this one. And of course I have a 2m omega h bar term as well. 2m omega over h bar. So I get 2m omega over h bar. This just goes away. And of course there is I have to take the square of this. There's a minus 1 here as well. So this minus 1 just goes away. So I get this term, right? This is what I get over.
The first expression to the 4 alpha squared is with the cos terms and not.
Sorry?
Like the 4 alpha squared term is with the cos squared term. So only plus 1 would be.
I can put this out, right?
No.
I can put this out.
mean to say that 4 alpha squared is with the cos squared terms in both. The 4 alpha squared term is with the cos squared terms.
Right.
So only plus 1 will remain after the subtraction.
Alright. Okay, let me write this down again. To avoid it. So my delta x squared is x hat squared minus x hat expectation value squared. Now what is my x hat squared? Is square of that is that term h bar 2m omega alpha plus alpha star is given by this. So I have a 4 alpha squared cosine squared omega t minus delta plus 1. Okay. Now h bar 2 m omega is present with this 1 and minus, what do I subtract? I subtract the square of this. Minus 4 alpha mod square h bar 2m omega cosine square omega t minus delta, and I'm left with h bar 2m omega. Correct? Okay. Likewise, my delta b squared is that term minus 2m omega over h bar into the square of this term, which is plus 4 iota square, which is minus alpha mod square sine square omega t minus delta, and of course there's a minus 1 here as well, and from this I will subtract the square of this. The square of this is 4 plus 4 alpha mod square sine square omega t minus delta. Now this becomes a 1 here, and I'm left with 2m omega over.
So there is a square in the first and second bracket. Maybe it's 4 alpha squared.
4 alpha. Right? H bar would be m omega. Definition आपने ठीक ही लिखवाई m omega. ये m omega of H bar. m omega h bar हो, ठीक है, क्योंकि हमारी डेफिनेशंस ये हैं. x ऑपरेटर इज h bar over 2m omega. ये मैं आपको एग्जाम में दूंगा a plus a डायरेक्ट, और p ऑपरेटर इज 2m omega h bar over a minus a diagram. Right? This I am providing you in the exam. Okay? So there is an m omega h bar over 2. So our delta x and delta p we have already found out. So delta x squared into delta p squared, what is this equal to? This equals h bar squared over 4. For this coherent state which is evolving with time. And what is delta x delta p equal to that? H bar over 2. So is this a minimum uncertainty state? Hence, what should this form look like? Gaussian. So it's a minimum uncertainty state, and this delta x, even if you put a time parameter here, you will observe that the uncertainties are independent of time. So at each point in time, the wave function looks like a Gaussian. It's a minimum uncertainty state. So now if I draw the harmonic oscillator, for a particular value of alpha, I will have a Gaussian. Suppose I am drawing the Gaussian in the position space. So this is psi x, or this is the inner product of alpha with the position state x. This is the representation of the coherent state in the position space. It looks like a Gaussian. There is a spread to this Gaussian. That spread is delta x. That delta x is given by the square root of this. Again, this is called the standard quantum limit, by the way. This fraction, SQL, the standard quantum limit. This is your uncertainty in the position measurement. So there will be a certain spread of this wave function. It's a Gaussian. It's not the ground state of the Hamiltonian. The ground state of the Hamiltonian, which is the vacuum state, is also Gaussian. But that doesn't change with time. The difference is that this Gaussian state is actually evolving with time. And it's oscillating with the frequency omega. Because you've already noticed that its expectation value for the position is changing with time. It's oscillating with the frequency omega. So with time, this wave packet is inside the harmonic oscillator. It's inside inside a well, and it's changing its position with time. Right? And then it comes back. And you can find out the time period of its oscillation. The time period of its oscillation is simply given by 2 pi over omega. And it has a certain phase where it starts operating. So this wave packet is oscillating inside the potential well. This is actually a picture of its time-dependent position. It's oscillating inside the well without any dissipation. This Gaussian is not spreading or dispersing in time as we have for a wave packet. If a wave packet in free space, with time, it's propagating, it disperses. But this is dispersionless. In other words, if we have a pendulum, a simple pendulum, it's oscillating with the frequency omega. It's not damping with time. It just keeps on oscillating with the frequency omega. So such a system is modeled by a coherent state. It's oscillating in the close proximity of the two classical damping points, within that range, the proximity. And its oscillation frequency is omega, which is defined as the natural frequency of the classical system. And it's a minimum uncertainty state at all times, which means it's a Gaussian. The state ket 0 is also a minimum uncertainty state because it's a Gaussian. But it's not oscillating with time. We know that this wave function is a stationary state of the Hamiltonian, whereas the coherent state is not a stationary state of the Hamiltonian. Now there is another way of generating these coherent states. Okay, one question that I would like you to do on your own is, I've defined the coherent state as the eigenstates of the lowering of alpha. Right? Can I define an eigenstate, some beta, of the creation operator? Try this out. Well, what's so special about the eigenstates of the lowering operator? Why can't I choose an eigenstate of the raising operator and define a new state? Now, if you work this out, you find out that this is impossible to do. You cannot choose a beta, you cannot choose a set of coefficients for the number states inside beta so that this condition is satisfied. Just try this out. Alright? This is something for you to do on your own. Now I also have a simulation, but before I move on to the simulation where I will show you these states in action, I would like to take in the next 5 minutes another view of coherent states, in which a coherent state is presented as a displaced vacuum state. Okay. Another thing that I would like you to understand is the meaning of alpha. Since there were questions about the meaning of alpha as well. If you have the number state n, and you're talking about a cavity, then this n would actually represent the number of photons in the cavity. Okay. Now, I've given in homework a question is that if you have a coherent state, what is the expectation value of the energy of the harmonic oscillator? And I would also like you to investigate the meaning of alpha. What is alpha? How does alpha tell you? How is alpha is actually related to the expectation value of the energy, and it must be somehow related to the number of photons in a cavity. This is something for you to explore on your own. For example, for a harmonic oscillator, we know that the energy is going to be h bar omega small n, where n is just the eigenvalue corresponding to the number state, small n, and it's also called the number of photons, plus half. What's the expectation value of a coherent state, of a system that has been prepared in the coherent state? You will notice that this n is related to alpha modulus squared. Okay, this is something for you to figure out on your own. Another thing that I would like to talk about for just for 2-3 minutes is that if I define now my x, I've defined my x as a h bar of 2 and omega a plus a dash. Okay. Now this operator has dimensions of position. If I would like to convert this into a dimensionless operator, so I can define a dimensionless operator. I can label it with capital X, and I define it as half a plus a. Okay. Likewise, I can define a dimensionless momentum operator, half iota a minus a dash. But sometimes these observables are also called quadrature fields. And you can find the uncertain, the combination of capital X and capital P, right? So this is simply going to be half 1 over 2i a plus a dagger a minus a dagger. Correct? So this is going to be 1 over 4 iota square, which is minus 1 over 4. The commutator of a with itself is 0. The commutator of a dagger with itself is 0. Commutator of a with a dagger is 1. But there's a minus sign here, so minus 1. The commutator of a dagger with a is minus 1. So I put a minus 1 here. I get 1 over 2. So the computation relationship between these dimensionless observables is 1/2. Now I also know from the principle of indeterminacy of quantum states, delta x, delta p must be greater than or equal to 1/2 of the expectation value of the commutator of the observables corresponding to these variables, right? So now, if the coherent state is a minimum uncertainty state, then delta x and delta p will also be at the minimum uncertainty state. So delta x, capital X, I'm talking about capital X, the quadrature fields equals 1/4. So this is another way of saying that it's a minimum uncertainty state. When we define new dimensionless variables, capital X and capital P, the uncertainty turns out to be 1/4. The product of the uncertainties. Sorry? चलो ले आएंगे बाद में, लेकिन उसकी एक्सपेक्टेशन वैल्यू नहीं है, ठीक है? तो अगर मैं एक डायग्राम बनाऊं, अनसर्टेनिटी डायग्राम बनाऊं, जिसमें ये x वेरिएबल, ये p वेरिएबल रखूं, then this minimum uncertainty state has a certain projection along x, right? It will have a certain spread along x, and it will have a certain spread along p. I can draw a circle here to represent the coherent state, and the circle is such that this product multiplies with this product, right? This is my delta x for this state, this is my delta p for this state. If I take the product of these states, I will get 1/4. So this can be a half, this can be a half. This is how I represent a coherent state on an uncertainty diagram. Of course I can use small x here and I can use small p here. The only point is that then this will become, the product of these will become h bar only. But that's simply inconvenient. So this is the minimum uncertainty state or the coherent state represented on an uncertainty diagram. And what I could also do is, I have to preserve this relationship. So in experiments what they can do is they can make this go down, and but at the cost of making the uncertainty in p go up. So they can make states of this kind, whose uncertainty in along the x quadrature field is smaller and the uncertainty along the momentum quadrature field is larger. So this is an example of what is called a squeezed state. You can have squeezing along the other dimension as well. You can have a squeeze state along the momentum variable as well. And how does a coherent state change with time? If this is my dimensionless variable capital X, this is my dimensionless variable capital T. Coherent state, of course, is represented by a circle, a perfect circle. Can you tell me how does this change with time? What does the uncertainty diagram look like with respect to time? Will the circle squeeze or will it expand? No, because the product of the uncertainties always remains constant. But this state is actually changing in with time. So what happens with time is that it goes around the circle. Because the expectation value of this variable is changing sinusoidally, and the expectation value of this circle of this variable is changing sinusoidally. So this field is actually moving around this uncertainty diagram with time with the frequency momentum, going round and round. Can you stay up till 9:30? We'll have a class. So I would like to
सर स्क्रीन से लगा
क्लास कितने बजे? 9:30 को कहाँ पे क्लास नहीं है, प्रॉब्लम नहीं है इसमें ये नहीं। If I have the ground state cat 0, if I apply a translation operator on this through a distance t, now what is the translation operator? Is e minus I p operator d over h bar. Actually means 0. Okay? Now what do I get? Now my P equals, once again I would like to write down my P equals, क्या है? Momentum operator is m omega h bar over 2, right? A minus A dagger. So this becomes, now what I'm doing, I'm displacing the quantum state in its position variable or in its momentum variable? In its position variable. If I take the wave function, in position space, that is I project on x, I will get the initial wave function displaced by t. This is what this translation operator is. So if e is for minus I, instead of p I write m omega h bar over 2 factorial d over h bar a minus a dagger acting on cat 0. Now is cat 0 an eigen state of A? No, it's not. Is it an eigenstate of A dagger? No, it's not. Right? And does A commute with itself, with A dagger? No, it does not. So I have to find out this, the new state that emerges out of this. Okay. So this is something that I'll do in the next class because it will take about 10 minutes. However, कितनी चल रहा?
चला है सर, आ रही
इसमें नहीं है, इसमें पावर नहीं है। और फिर अगले हफ्ते से हम 3 डायमेंशंस में जो